So it's recording right now. And if you look back at your D2L webpage, you will see that the lecture material, if you click on the lecture from Tuesday, here's the video. And so you can go back and it's on YouTube and you can watch it and review things. I did this because I did this when I was at North Carolina State University. I was at North Carolina State teaching a class like this for many years, and they love having the videos of the classes afterwards. Even though I know that by doing this, some of you are already thinking the little gears are turning your head. I don't have to come to class now. But I realize that, however, hopefully I make the lectures interesting and useful enough that you still want to come to class and have the videos. Okay? That's my goal. So the videos are here so that if you get confused by something, you can go back and take a look. It's especially useful before the quizzes and before the final exams. Is everybody happy with this? Okay. All right. Then let's go to the new material. All right, so first thing I want to cover is the notion of a turning point. And to get used to this chair, it's a little too high. Turning point. It's basically where something turns around. So if we have let me make a plot of position versus time. Let me make this box go away. So if I have x, position, t, time, and if I plot something like this, okay, what's happening is, so let's say this is positive x, then as a function of time, right, it starts increasing in x, and then at some point here at the top, it doesn't keep increasing, but it momentarily is at rest, and then it turns back. Okay. So that's what's called a turning point. It's like when I'm walking, I'm going this way, and then I slow down, and then at this moment, and I'm at rest, but then I go backwards. So this is the turning point. And so I can explain in words that it's the place where the position is a relative maximum or minimum okay, and the instantaneous velocity is 0. Okay, so that's the notion of a turning point, where the position is a relative maximum or minimum, and the instantaneous velocity is 0. It's where you basically turn around. So relative means in this vicinity of that point, it's the highest or it's the lowest, as opposed to, maybe you remember from calculus, relative maximum, relative minimum, versus absolute maximum, absolute minimum. Remember those terms? Okay. Are there any questions about this concept? Okay. Yeah, that's it. Oh, I'm sorry. I didn't even notice that. Somebody had turned off the. Why is that not working? Okay. Left projector. Both projectors. Right projector. Right projectors. Okay, so I got you. Turn. Okay, I'm going to turn off. I'm going to turn it on. Oh, turned off both of them. Crap. Okay, let's hope that this. Let me talk while I'm waiting for the projectors to turn on now. Okay, so what we're going to talk about today is last time we talked about velocity is the change in position versus over time, right? Delta x over delta t. Talked about average velocities for a given time interval is delta x over delta t, and then the instantaneous velocity is when the time interval is very small. And then we talked about, we can think about as delta t goes to 0, the instantaneous velocity is the time derivative of the position, right? dx by dt, dx over dt. What we're going to talk about today is we can, we'll do several things today. Hopefully the projectors will do something soon. 22 more seconds. We'll talk about if we have a plot of the velocity now versus time, how we can get the displacement. Okay. All right. Let's see what's happening. 3, 2, 1, and then it's going to turn off and then turn on. Remind me never to touch the projectors in the middle of the lecture. This is a dangerous thing to do. (14:13). And let's see what actually happens now. Okay. Okay. Yeah, it thinks both projectors are on. I don't think I'm going to be able to fix this at this time. So, okay. Yeah, sorry, we're going to have to live with this. But I'll put it. I'll stop by the physics department's office to see what's going on with that guy. I'm not sure what the deal is. Probably the bulbs are out or something. All right. So you're talking about the instantaneous velocity. So when we have the instantaneous velocity, okay, we said that we can write this as v, and this time I'm going to put v of t to remind you it depends on the time. And we said that it's the time derivative of x, and again I'm going to put the t to tell you it's a function of time. It depends on time. Now what we're going to do is we're going to remember some calculus stuff and do integrals. Okay, so what we're going to do is we're going to integrate both sides. Integrate with respect to time. And so I'm going to integrate dt, but I need an initial time, ti for initial, tf for final. And we're going to integrate the left side, so I'll have v of t dt. So I'm doing the time integral of the left-hand side from ti to tf. And then I'm going to do the same thing for the right-hand side. T. Okay. Does anybody know what the integral of dx by dt with respect to dt is? Otherwise, how do you do that integral? Yeah, it's really easy. What do you get? Yeah, you just get x, right? Because that's how you do integrals. You say, what function, when I take the derivative of it, gives me the thing in the integrand, right? And you're just staring at it. The function x gives the derivative. right? The way I've written it. So this is what's called the fundamental theorem of calculus. Remember that? Hearing that in your calculus class, this really obnoxious, pretentious thing, fundamental theorem of calculus. So that's what this is. So you get x of t, and it has to be evaluated at the endpoints. So you just stick in the value on the top minus the value on the bottom. But we know what we will call this. This will be x final minus x initial. Okay, and so that's just going to be delta x. Does that make sense to everybody? Okay. Maybe this is a bit dim. I'll boost up the lighting. Does that help? No, that helps. Okay. Any questions about this? All right, let's go on. So what we find is that the time integral. Okay, so let me just make a plot. Suppose I have the velocity versus time. So v is the velocity versus the time. So let me write it to make sure you realize I've made this the velocity, the instantaneous velocity. And so let's say I have a curve of the velocity versus time, and I have some initial time, ti. I have some final time, tf. Okay. And if I do this integral, ti, tf, v of t dt, that is, in terms of graphs, that will be the integral. This integral will be the area under this curve, right? That's what calculus, what the integrals are doing. So this area here is that integral. So this is the area under curve. And we said is equal to this time integral, v of t dt. But we just wrote that this is equal to delta x displacement. Everybody following me on this? So if you're given the velocity versus time, and you get the area under the curve between two values of time, that will give you the displacement that the object does in that time interval. Okay. Any questions? Yeah, instruction or question? Okay. All right. So we can do the same thing if we want for acceleration. The time integral of the acceleration gives the change in velocity, delta v, rather than delta x. So what I'm saying is, if I take the acceleration, which is a function of time, instantaneous acceleration, and I do the integral from ti to tf, okay, because the acceleration is just the time derivative of the velocity, v of t derivative, dt, we know how to do this integral, just fundamental theorem of calculus again. And so we end up with v final minus v initial, so that's delta v. Right? Does that make sense? I'm just trying to put this together so that you see the parallelism. Okay. Everybody, is anybody confused? This is not supposed to be hard. It's just if something's a derivative of something, like if g is the derivative of f, right? Then if I integrate g, I get f. That's all I'm doing. Okay, so then similarly, if I have a plot of the acceleration versus time, t, and it's a curve like this, then the area under the curve, this area, is equal to delta V. All right. Are there any questions about that? Okay, very good. Let's see. Now at this point, let's switch things up and get out your clickers. Let's do an example. Okay. Let me just go directly from the notes on this. I don't have to copy it again. Let's go. Here's an example. Okay, let me read it. The position of a particle is given by the function x of t is equal to t cubed plus 2t plus 4. Now, in order for this equation to have the right units, I have to say something sneaky like where the time t is in seconds and the position is in meters, okay? Just to make units. So the first part will be, what is the displacement during the time interval from 2 seconds to 4 seconds? And I will open up the polling for this. So put AA, well, if you need to do this again, hold down your power for 2 seconds, press AA, and then go ahead. Yeah. Oh, okay. Oh, yeah. So we got it. That's a good point. Had we? That's too small, though. Maybe. Does that work? Okay. What I'll do is I'll rewrite these numbers so you can see 16, 24, 36, 60, 76 meters. Can people see that in the back? Okay, all right. Yeah, it's t cubed. It's a cube here. Like, this guy's a cube. I just want to see how visible this thing is. Cool. Dark. Okay. Pretty had a chance to make an answer. I don't want to rush you, but at the same time, don't want to take all of the lecture time. So I'm trying to figure out what the happy middle is here. You know that you said this. Okay, so let's take a look what people have said. I'll close it up now. Go ahead, click in if you haven't yet. Okay, let's stop it now. Let's see what people have said. Okay, a lot of D's. Let's take a look. Okay, so let's write down the function. Okay, the function is x of t too hot is equal to t cubed plus 2t plus 4.0. Okay, and so this part of the problem, we say t initial is equal to 2 seconds. And so if I want to figure out what is the initial x, let's call it xi, then I plug in 2 for my t, cube it, and then I have 2.0 times t, which is 2.0, and then we have 4.0 is on the end. So we have 8 plus 4 plus 4, that's 16. And then we have t final is equal to 4.0 seconds. So x final is 4.0 cubed plus 2.0 times 4.0, because that's what t is, and then we have a 4.0 on the end. So we have 4 cubed, which is 64, plus 2 times 4, which is 8, plus 12, plus 4, which is 4, okay? So we have 64 plus 8 plus 4, that's 76. And so we want the displacement, so delta x is x final minus x initial. So 76 minus 16, that's equal to 60 meters. Okay? Any questions about that? You got that? Okay, let's do the second part of this problem. The second part of this problem, let me put it here. And what I'll do is I'll write down the function again. So it's t cubed plus 2.0t plus 4.0. It's the function, okay? And I will open up the polling now. Oh yeah, let me read it to you. So what is the instantaneous velocity at time t equals to 2.0 seconds?